So yesterday we ended by beginning, that sounds weird, towards the end of the lecture yesterday we started to talk about this, how we can generally handle piezoelectricity and piezomagnetism. They actually are part of a whole of a basic thermodynamic approach that can be taken. And this is useful, as we'll see. So here's the idea. We look at the, this is the energy, remember the energy per unit volume. I'll change that. And you're familiar with part of this. The change in energy of a system done by work is the pressure times the integral of the pressure times the volume, where a small change in energy would be minus PdV, as we discussed yesterday. You can also change by adding heat. This is heat right here. And now because we have more than just tensile changes, we have possibility of shear, work done by shear. This gets expanded here beyond the minus PdV. And also we've got electromagnetic field energy. That's what this represents. So, so this is the changed energy per unit volume. And remember, the repeated index here means summation, right? That's the Einstein summation notation. Now, it turns out that for most of our work here, oh, you can, excuse me, you can see that the energy here is a natural function of the stress, the displacement field, the magnetic field, and the entropy. It turns out that the variables, typically the convenient or natural independent variables for us are actually the flip of all these. It's actually the stress, the electric field, the magnetic intensity, and the temperature. It's better for us to think of those as the independent variables. So we can make that switch with what's called a Legendre Transformation. I didn't write that in here. But what you do is, and this is pretty well known in thermodynamics, you may remember it, instead of the energy, you consider a related function. They're usually called thermodynamic potentials. And in this case, we want to deal with what's called the Gibbs function. Do you guys remember this? Does this look familiar? Maybe not. So all it is it's really a transformation. Instead of the energy, we're going to deal with this function, which is the energy minus these quantities here. And the reason, it's easy to see why you do that, okay? This is called a Legendre transformation, and it's easy to see. When you take the differential of G, take the differential of U, you're going to get this, right? But now you've got to take the differential of all these products here. That's going to give you two terms here, two terms here. And you can see, and you can do this in your head, that one of the ones here is going to cancel this. And what the effect of that is instead of dealing with S is the natural variable here, you're now going to be dealing with T. So it's actually really simple. You know, it's surprising that somebody's name is attached to it. And incidentally, it occurs not only in thermodynamics, it can occur in advanced mechanics, classical mechanics. I saw that a few months ago. So anyway, the same thing happens here. So what we're going to end up with, and again, like I said, you can just do this in your head. You don't need to write it down. The differential of the Gibbs function is equal to this. So the Gibbs function is a natural function of the natural independent variables are the stress, the electric field, the magnetic intensity, and the temperature. One of the reasons this is useful, for example, and I think I might have mentioned this yesterday, is if the temperature is constant, then you don't have to worry about this term. But if you want to deal with constant temperature up here, you're out of luck, okay? You're going to have to deal with it, and the entropy can change. So you can see that's one advantage to using convenient independent variables. Okay, so we're going to deal right now with G, because these variables turn out to be convenient for us. There's something else, there's something we can get from the differential here, this form. And we could just as easily do it from here. It really has nothing to do with the transformation going from here to here. But we're going to deal with G because these variables are more convenient for us. You'll notice here, this is what's called a perfect differential. And I think it's best for me to, I meant to write this on the board. I think it's better. Let me give you just the simple math here. It's actually really simple, and you've probably all seen it in introductory calculus. Consider a function of two variables, okay? This is just in general math here. You know that the differential is going to be some function. It's going to look something like this, where this f function is, of course, the partial of h with respect to x, and the g function is the partial of h with respect to y. Okay? Now, you can see here that if I differentiate f with respect to y, I'm going to get the second derivative of h with respect to y and x. If I differentiate g, on the other hand, with respect to x, you consider these two derivatives. You can see that the right-hand sides are the same because it doesn't matter the order in which you differentiate h. So we get this condition here. And you probably, if you remember this at all, you probably remember it under the name of, it's the condition for a perfect differential. If you, in general, you write two functions like this, this is not, you can't in general express this as a differential of a single function. When you can, it's called a perfect differential, and this is the condition that has to be satisfied. So there's different ways of looking at this. For us, and this is what happens in thermodynamics, this happens in thermodynamics too, okay? And it's important here, as you will see. Instead of this little h, we've got g, and it doesn't matter how we differentiate it. So, for example, I'm going to assume there's no magnetic effects and no temperature effects. Just kill this, okay? Just to see what's going on here. So for constant h and constant theta, we have this. And because the second derivative of g, it doesn't matter the order in which you differentiate, we end up with a relationship between these two quantities. And that's important because this quantity right here, the partial of s, how s changes with E, that's important. How the strain changes with electric field, that's important for us, right? It's transduction. And it has a name. It's called the Piezoelectric strain constant, and it's universally denoted by the symbol lowercase d. And so we have here, just from this math, from the perfect differential, the second derivative thing we can do here, we have that we can express this piezoelectric strain constant in two different ways. Here's the way that we usually think of it. It's how the strain changes when you change the electric field. But it's also identical to how the displacement field changes with stress. So if you didn't know this, you might think that, and you encountered this, you might think that these are independent quantities. You got some material, it'll have this value, you usually look it up. Okay, if you can't, you have to measure it. And you might think this is some independent quantity. It's not. They're mathematically identical to each other. Incidentally, the notation is getting really kind of thick, or I don't know what the word is here, heavy. So these are the indices on D, as we've seen. The superscripts here means that h and theta are being held constant. Sometimes that constant is 0, it could be 0h. It's probably not going to be 0 theta because that's absolute temperature 0, but in general you think of these as being held constant. So this is, you can actually think of this as a kind of generalized reciprocity. So remember I told you, I think yesterday, I see reciprocity everywhere now. And you can see it here now. This is a stretch for reciprocity. You've got to change your canonical variables. You know, reciprocity has to do with interchangeability, right? Of sort of the drive and the source. You've got to change your canonical variables when you do that. But you know, it's still a kind of reciprocity. Now we just did it. We just did it for G here. We got that relationship just for these two variables. You know, what about these two? Oh yeah. Yeah, these two, yeah. There's a total of 6 possibilities for the G function and any other thermodynamic potential. You know, you can do the same thing with U. So here they are written out. The 6 possibilities for the Gibbs function. Here's I just reproduced this. Okay, there's the piezoelectric strain. There's an analogous piezomagnetic strain constant. Okay, how you stress the material with magnetic with magnetic intensity. That's the analogous to D. There's these the pyro things, you know, for temperature here. So there's these two quantities are identical. You don't have to treat them as independently. So you can imagine how useful that is, especially if you know you're at the National Institute of Standards or somewhere where somebody has to determine these quantities for different materials, and you hope it's not you. You hope you can just look these up, or you know, maybe, or call somebody up and try to get them to measure it, because it takes time to do these things, and if you need them accurately, you know, it's something that I always really try to stay away from. But there are some people who love to do that, and they're good at it, and they're all at the National Institute of Standards. Well, there's more of them, but you know, that's their job, right? Is to determine quantities accurately. So there's a pyroelectric and an analogous pyromagnetic. And there's another quantity here, the magneto-dielectric constant. And finally, we all know this one. Look at this one. This is how a material strains when you change the temperature. And you all know what that is. That's the thermal expansion coefficient. And so it turns out here that the thermal expansion coefficient is also given by this, how the entropy changes with stress. Incidentally, this is standard notation. The subscripts here refer to what you hold constant when you do this derivative, right? Now there are other quantities. While Brian mentions these while we're at it, there are other quantities of interest besides these here. Here's the, we've already talked about this. Little s, remember? UCC, right? So these are the compliance coefficients. We can think of them in differential form. This just comes from the fact that the strain is the compliance matrix times the stress, right? So we can think of these quantities in a differential form here as how the strain changes with stress here. We can do the same thing with a dielectric constant, you know, because D is equal to epsilon E. We can do the same thing there. And the analogous magnetic case, right? And then finally, here's something you'll all know, the specific heat. It's given by this. It's how much, to change the temperature, it's how much heat you have to add to change the temperature by a certain amount. And this is a per unit mass, that's why the rho is there. This is the heat, TDS, in normal thermodynamics. There's the temperature. Okay, so why do we need all these constants? Well, it's kind of, I think it's probably pretty obvious that, you know, we're going to have to be dealing with these, but you can see it explicitly when we look, let's say, at the, let's look at the strain. Okay? So we can think of, we will often do this, we'll think of, we're just going to be focused on this, as you'll see in a minute, but proceeding in general here with the basic thermodynamics. If we look at it, see how the strain changes as a function of the independent variables T, E, H, and theta, we can generate this Taylor expansion, this approximation here. So a change in the strain due to the stress will be given by this. You want to multiply by this coefficient, right? This is just a Taylor expansion. And these quantities are what you see on the previous page here, so we can write them like this. Now we can take this one step further. If the over the range of stress change and electric field change, etc., if these coefficients here are constant, then we can immediately integrate this and find the strain. And we can do it for, I've just chosen S here. We can do it for the other independent variables too. In this case, these were, dependent variables. We're thinking of these as independent variables. Then we've got these other 4 dependent variables. The strain is one of them, the displacement field is the other, etc. So we can integrate all of those. We can come up with expressions here for the strain, the displacement, magnetic field, and the temperature. Now when we integrate here, we're really integrating from 0. So usually you don't want to integrate temperature from 0 because you're probably not interested in absolute 0, being way down there in temperature. So I put deltas on the temperature here, and associated with that is the entropy too. We're just putting this down for completeness. I don't think we're going to deal with this for the rest of the course, okay? But this is the general treatment here. And there's a huge amount of bookkeeping here. How many equations is this? Well, you remember how many different stresses are there? How many different strains are there? There's 6. Remember? 3 tensile, 3 shear. So this is 6 equations. This is 3 equations, 3, and 1 equation. So there's 13 equations here. And this is, we're not modeling some specific system. This is a fundamental physical theory. So I've never seen any, including general relativity, I've never seen it as complicated as this for any fundamental physical theory. Of course, it contains a lot in there. We've got elasticity, we've got thermal effects, right? We have electromagnetic effects. It contains a lot. Now, this is not a big deal, but it may come up, and it's minor. As I mentioned before, it's natural if you use these, they're good if you've got an isothermal situation, because then you don't have to worry about this term, these terms right here. All the delta theta terms are not important because delta theta is 0. However, in acoustics that there are temperature changes, but it's adiabatic. So you would actually rather have a delta sigma there, okay, the change in entropy, because then that will be 0. So it's actually, for acoustics, it's usually more convenient to do that. So there's 2 comments that can be made about this. First of all, it turns out that the difference between the two, in our case, Sonar is not very much. That's one thing. It turns out just not to be much. The other thing is that if you wanted to do this, you can, if you wanted to switch from temperature to enthalpy, you can go back and look at the energy, or because Gibbs is so popular, the Gibbs function is so popular here, you can do the following. You can make a transformation, a Legendre transformation on the Gibbs function. So instead of G, you consider this is called the enthalpy, and this is the Gibbs transformation. This is changing the independent variable, right? Because when you take the differential, you're going to kill whatever's in there, and you're going to switch it. So this is the way people usually look at it. The enthalpy here. Let's see, what did I... Hold on. Yeah, so when you use, instead of the Gibbs function, you want to consider the enthalpy, which is the Gibbs function plus sigma times theta. You'll then find that I mean, and it's obvious. When you take a differential, this is going to switch the independent variable from theta to sigma. Okay? So then for acoustics, if you want to be accurate here, d sigma will be 0. So you simplified the description. Okay, so this is a grand scheme here. It's got all kinds of stuff in there, including pyro effects. What we're going to be dealing with is this upper left quad right here. Okay, we're not going to worry about, for right now, about magnetic effects. And typically in piezoelectric material, the magnetic effects are small. And there can be pyro effects, but they're typically small too. So it's often a good approximation in piezoelectric material to just kill all this stuff here, and we just deal with this. So it looks a lot better, right? So you're going to become well familiar with this in the next couple of weeks. And I will mention to you this. We're going to strain this out as long as we can. Eventually we're going to have to deal with different independent variables, and you'll see why. But for the time being, I think this is sufficiently complicated. We're just going to stick with T and E as our independent variables. So here they are. Now, we're going to write this in vector matrix notation. This is a 6 by 6 matrix, right? This is just, these are elements here. This sum here, you got to sum over J because it's repeated, involves this 6-dimensional matrix. This is a 6-dimensional vector. So in vector matrix notation, we can simplify this and write it like this, right? So this is a 6-dimensional vector, 6 by 6 matrix, 6-dimensional vector. You want to think of these as vertical. It's the convention here. And then the important, this is the transduction term here, right? It's a matrix too. I'm going to talk more about that in a minute, and I'll talk about why that T is there. But I want you to look at those equations. You've essentially seen this before, actually many times. And the key is to look at these two terms right here, and don't worry about the T right there. We've got we've got transduction here between elasticity and electricity. And what kind of a transduction is it? It's reciprocal. Okay, you see this coefficient is going to be, it's the same as that. So these are actually the form of the canonical equations. And with bookkeeping, right? These aren't scalars. This is a vector, 6-dimensional vector, and these are matrices here. All these lowercase things are matrices here. Now, there's a little bit of a problem here. The electric field is 3-dimensional. The elastic field, if you want to think of it that way, is 6-dimensional, right? So D cannot be a square matrix. Okay, D has to actually be, if you look down here, this is where the transduction is. It's going from 6 dimensions to 3 dimensions. So this is what D is going to have to look like. It's actually a 3 by 6 matrix. And so here, what we're forming is this product here, as we mentioned yesterday. The meaning of this D times T is it contributes to this 3-dimensional vector here, and the x component is the inner product of these two vectors. So you take this times this plus that times that all the way down, and you put the value in there, and then you redo it there and there. And you can see here, if we didn't have this little t here, which stands for transpose, you cannot do that. You cannot take a matrix like this and multiply it by a 3-dimensional vector. It's nonsense. But it does make sense, and you can prove, if you go through and carefully look at the subscripts, you can prove this, but it's really obvious. That what you have to put here is the transpose. Now you can do it. That's the way out. And that's what a proper treatment shows you, but it's pretty obvious. So in this case, typically what people do is they'll signify that we're dealing with a transpose there. Even though it's implicit, even though the only way you can make sense of this is dealing with the transpose of D. Okay, but they still often will put it, right? In other cases, it won't be put. For example, you know, we'll deal with this. This is simply this vector, but horizontal instead of vertical. We won't write this. Okay, it'll be clear. We may be pre-multiplying by t. You know, we might be multiplying t times some matrix here. And in this case, you want to think of this as horizontal. We won't write the transpose there. It's understood. And again, you're even forced here. You know, you really don't have to write that, but people do because because it can cause trouble. I suspect that's why they do it. We want to make it clear, explicit in that case. Okay, now, if you look in the book, you'll see there's a lot more on this. And what it is Brian takes this opportunity. I don't view it as an opportunity, okay, but he views it as an opportunity to not just write down these equations here. These are equivalent, okay, not just to write these down for when you have t and e as the independent variables, but to look at all the other three cases. Okay, so we have t and e. You can also use, you know, we have these 6 variables here. Here are the 6 variables. Okay, and they're you know, they're grouped in pairs. You know, s and t go together, e and d, right? Yeah, S and T and E and D. So you can, this is T and E as independent variables. You can choose any pair, but you know, you can't choose purely, you can't choose S and T because you don't have any electrical information there, right? So you got to, of course, mix the two. So you're going to get 4 possibilities. The other 3 are S and E, T and D, and S and D. And so what you do is, and you can all do this, given enough time, you could re-express this in terms of, let's say, S and E. What's going to happen to these coefficients here? Well, it's going to get complicated. So what people do is they just call those a different symbol. So all these other forms look just like this, okay? You'll have, you know, instead of this, you'll have like S and E. Let's say we want to switch T and S here. And then this will be called some other symbol. So that's telling you something. It's telling you that people use this stuff, you know? They don't want to drag around. They don't want to solve for this coefficient here. When you manage to make this S and have T over here, you're going to get some function, you know, some non-trivial thing here. They don't want to drag that around, so they call it a symbol. So it's telling you that we just can't stick with these independent variables. We're going to have to deal with the other ones, and we will eventually. But we're going to put it off. What I decided when I first went through this was I didn't want to worry about it. I had enough trouble trying to understand this. So we're going to postpone this as long as we can. Eventually, we will have to do it. And then I'll remind you, you can go back to this chapter and look at Brian's expressions for all the other possible independent variables, okay? All right. Oh, here's something that bothered me. What we're interested in here are really we think of this, you know, as this is a function here. The strain is a function. What we're really interested in what we are really interested in is in changes of the strain, obviously, right? But it's not convenient to deal with a change in a quantity because then you have an initial and a final. We just want to deal with one quantity. This happens all the time in physics. So it's understood here that this is the change from equilibrium. Usually that's all we're going to care about is the change from equilibrium. In equilibrium, there can be some stress. In equilibrium, if you have a piezoelectric material, which is like a capacitor that's been electroded, as you know, and we're now starting to get into the proper treatment of this. But earlier it was introduced to you, the simple idea of piezoelectric material. It's useful in transduction. You take this piezoelectric material and plate it, put electrodes on there. I forgot what I was going to say. What was I
Equilibrium.
Right, thank you. One word, thank you. So, and we can, for example, we can put, and you've done this in the lab, put electrodes on here and drive this thing, okay? Well, when you're not driving it, it's going to be in equilibrium. We're going to find that to be useful here, this piezoelectric will actually have an equilibrium electric field in it. There will be an E naught, okay? And there will be stresses. It can be stressed, it can be strained. There will be an S naught. But it's just not going to be relevant for us. So I need to edit this. I didn't quite make this as general as I should, but that's the point of what I've written right here, is that we will have equilibrium values here, but all we're interested in is the change from equilibrium. And I don't think Brian says this, you know, but I just remember that it bothered me. Okay. So, you know, now that I think about it, this approach right here is really, it's very impressive. This, you know, this general thermodynamics, way beyond thermodynamics, right? It's got electricity and magnetism and elasticity there. It's, to a particle physicist, it's kind of like a unified, grand unified theory, what they call. It's deeper when people talk about a grand unified theory. And I think I might have mentioned this. You know, thousands of years ago, people thought there was an electric, they saw electric effects and magnetic effects, and they just assumed they were completely separate. But then they were unified into one theory in finally in the 1800s, right? And then that was unified with the weak interaction in the 1900s. But this is not on that as deep as that, but it is a kind of interesting unification here that allows us to be very general in the treatment of things. And we really haven't done anything. It's really, you know, we haven't, you know, the physics here is, let's go back to, see this D here, how where does this come from? How does this occur, right? Where does it come from? Well, we haven't talked about that yet. We've just done like the bookkeeping here. We just set things up. We haven't really done any physics, I guess. That's a pretty strong statement. Okay, this is just all the mathematical machinery, but we'll get there. And it is, like I said, it is nice to be able to do this from a unified approach. Okay. So next is we're going to dredge this back up again. The coupling factor. Remember, it's K or K squared. The coupling factor is really important because it tells you, it's a dimensionless number that tells you the relative strength of the transduction. So usually you want this to be big. You know, you don't want to waste your time building some transducer out of some material that you may like for some other reason, but then you look up its K value and it's really small. Okay? So we want to look at the coupling factor in the context of piezoelectric transduction. We're going to consider here uniform. Uniform means spatially constant, right? Uniform strain and electric field. That's not always the case. If you got some transducing material and you go to high enough frequency, you're going to get standing waves in there. And we'll have to talk about these in this class. It's eventually. We'll put it off again These more complicated things we put off as long as possible, but eventually we're going to have to do it. But sufficiently low frequency, it's going to be uniform. Oh, also, I didn't realize, and it's not in here, but I'll edit it. The geometry makes a difference. It makes a difference. I'm thinking here, we're thinking here of rectangular geometries, but eventually, particularly for hydrophones, we're going to have to get into, you know, curvilinear coordinates, radial geometries, cylindrical and spherical. Very popular in hydrophones. So once you get into that, you don't have uniform fields anymore. So, but we're going to focus right now on just uniform fields, spatially constant fields. And we can do something interesting here to get at this coupling factor. We want to look at the energy. So remember, here's our energy, right? We're neglecting pyro and magneto effects. This is piezoelectric. And we can integrate this. Right? Now, so I want to integrate this with respect to S, but you know, the stress is going to depend upon the strain. We know the dependence is given by here, the Hooke's law thing, stress-strain relationships. So I want you to imagine, I need to edit this a little bit, but just, it's simple. Substitute this expression into here, and then integrate with respect to S. We're of course assuming these are constants. The stiffness coefficient, are you starting to see it? Yeah, it's the upside down glasses. So that's what they've made, right? They had these prisms they put on people, they made them into glasses. And so they would put these on, they did this experiment. So, and you guys have never heard of that experiment? Yeah, there's all kinds of interesting, like psychological sort of, or physiological kind of experiments that people do. And some of them they would not do anymore because they'd be considered cruel and unusual punishment. But so anyway, you're starting to see this now, I think. So we'll assume those are constants. Now we can integrate. Does this look familiar? This is just like a spring. I'll talk about a spring in a moment. But once we do the integration, we're going to end up with an S squared here. And then we want to go, it's convenient for us to then substitute this back in. So it's kind of weird. We substitute this expression, and this one too, to do the integration. And then we go back and put that in, and here's what you get. It's a nice, simple form. And we don't normally think of this, but you can do the same thing for a spring here. The energy in a spring is, right, 1/2, where K is the stiffness here, right? We all know this, it's 1/2 kx squared. We know that the force on the spring, so I don't want to worry about the minus sign here. This is the force on the spring is given by that. So from these two expressions, you can write that. How many of you have seen this in mechanics? You just won't see this in mechanics, right? But it's obvious, right? You can see it. You just take one of these x's and do that. That's what we've done here. And it's just for convenience. Apparently it's not convenient in mechanics, but it's convenient for us here in transduction. So we get this nice expression here for the energy. And the next thing we do to analyze this, and we're after the relative transduction here, we're going to substitute essentially our canonical equations. So we're thinking of S and D as dependent variables. So I can take these expressions and substitute them into the energy. And when I do that, I'm going to get 4 terms. This may start to sound familiar to you. We've been through this kind of thing before in the coupling parameter. When I do that, so when I substitute for this dependent variable S here using our canonical equations, I get 2 terms. I do the same thing with D. Okay, so I get a total of 4 terms here. All right, here's the purely elastic energy in the system. Here's the purely electrical energy, and the whole point of this course is we've got energy in this transduced energy. It's coupling the two, and here it is right here. And those look pretty similar, don't they? In fact, they're identical. Why are those identical? Now you got to be careful. Remember, these are vectors here. when you take the transpose, and all of you have seen this, you may not remember, but it's actually pretty simple. If you take the transpose of this quantity, you need to invert the order, and you need to, of course, transpose these. We don't put a t on these vectors. It's understood. But we do put it on the d. When I take the transpose of this, I'm just going to get that. This is a scalar. You can take the transpose of a scalar, and you're going to get the same scalar back, right? So I can freely take the transpose here. I'm not changing the value of this. So this tells us, because when I take the transpose of this scalar, I get that scalar. These are identical terms. That's just a reflection of the reciprocity. We have a reciprocal transducer. The energy that's going one way is the same energy going the other way. We'll call that the mutual energy, like we did before, going one way. So we have two contributions here, so that's why we doubled the mutual energy here. And this is, the two is just a matter of convenience in our final formula. So now we're there. The coupling factor, I guess they call it usually, the coupling factor is this dimensionless thing. It's going to be the mutual energy divided by a measure of these separate energies in the elastic and electrical case. So to come up with something that's symmetric, we multiply those things together and we take the square root. So I should have written this out here. Yeah, so here's our definition of the coupling factor. It's the mutual energy divided by the geometric mean of the elastic and the dielectric energy. And so we end up with this expression. Now at this point we can't, you've got to specify what's going on in your system. We just have to leave it like this. This is very general. We can look at the simplest case. The simplest case is where we just have, everything's happening in just one direction. We're going to call it the z direction here, but it doesn't matter. But it will be different in the different directions. And you'll get used to this in piezoelectric material. They are not isotropic. They're necessarily, as we will see when we get into the physics of piezoelectricity, they are necessarily anisotropic. So we have to deal with this. So right now we're just going to take the three direction. So we have just a stress and electric field in the three direction. All the other components are assumed to be zero. And it's very easy to see when you look at this. This is called a contraction. When you have this is a matrix and two vectors sandwiching it. You end up with a scalar. So that people call that appropriately call it a contraction here. In this contraction here, there's just going to be one term because we only have a T3 in it. We only have a T3. You can easily see that you're just going to pick out the 3,3 component of this and multiply it by the T3. So we just get this one term. In general, you could have more terms, but we just have one here. And similar thing happens here. We can simplify this, and we get this. Okay? And this is important. It's so important that often it'll be tabulated for different materials. So instead of you having to look all these things up individually, this is such an important thing. You'll see this in the book eventually. There can be values of this tabulated. Okay. So we're going to leave the mathematical machinery, we're going to leave it there for now in this chapter. And there's one more thing we've got to talk about. As I said, eventually we're not going to have uniform fields. Okay, we'll have standing waves. We're going to have to deal with standing waves. So we need to talk, this is just sort of a summary of waves in elastic waves in solids. And some of this you've seen before, and as I'll point out. Solids you can have compressional waves, and you can have, of course, shear waves. Okay, you can also have boundaries, and the boundaries can influence those waves. In fact, the boundaries can cause the wave speed to depend upon wavelength or frequency. What kind of waves are those? We have a general name for those waves. When the speed of a wave is not independent of the wavelength or the frequency, what kind of wave is it? There's a general word, dispersive waves. Okay? Acoustics, so far, acoustics is typically non-dispersive, or only very weakly dispersive. The speed of sound doesn't depend upon the wavelength, right? But you can have systems even without boundaries, like ocean waves, where, well, I guess there are boundaries there. But you can have systems that are fundamentally dispersive without boundaries. But boundaries can cause dispersion. But regardless of that, the general form of a speed of an elastic wave is this square root of the elastic, the appropriate elastic modulus divided by the density. So last quarter, it was the adiabatic bulk modulus. Remember? That was the speed of sound divided by the density. Take the square root. So a warning here, and the units work, incidentally. You can confirm that. When you have a boundary, what can happen is this elastic modulus can become frequency dependent or wavelength dependent. And that's how the dispersion gets in there. Okay, so let's go through these different, we'll start this today. We don't have to finish it. So, but let's begin here. There's a little bit more here. You want to remember Young's modulus, capital Y, we call it here. It involves, when you have Young's modulus, that elastic modulus, involving this compression and extension here, it allows the boundary, for the boundaries there, they're allowed to freely change, right? So you can have, when you compress it here, you have bulging, and vice versa. And the transverse motion is quantified by the Poisson's ratio. So for a certain displacement here, I'm going to get a displacement there. The ratio of that to that, which is dimensionless, is called Poisson's ratio. And it turns out, I keep putting off looking into this, but it turns out that Poisson's ratio is restricted for classical materials. There's all kinds of weird materials out there now that you've probably heard of. So I wouldn't be surprised if this has been violated. But for standard, ordinary materials, the kinds that we're going to be dealing with, okay, Poisson's ratio is restricted to within this range. This is really not important to us, but if you dig deep into these expressions that you're about to see here, you can get some nonsensical results if you don't understand that nu is restricted to this range, okay? So what happens when you have some of these modern weird materials? I don't know. But that's people are exploring that, right? So let's begin with no boundaries. Suppose we have no boundaries. We have an elastic wave with no boundaries. So, it's like an earthquake happens deep in the earth. Let's say it's something deep in there where it sends out a compressional wave. So you don't have to worry about the boundaries. What's the propagation? What does it look like? Let's say the wave is traveling this way. There's compressions and expansions. What's happening in this direction? Remember, we have essentially infinite medium here. It can't bulge, okay, with an infinite medium. If it bulges, if you assume you have an axis here, you have this wave going like this, and you get this bulging here. It's going to bulge. It has to bulge more and more. It has to be uniform that way. It'll go to infinity. So the fact that you have a very large extent of the spatial medium this way means that when this wave comes along here, the motion is purely going to be longitudinal. That's called unilateral compression and extension. And the modulus there, and I think I mentioned this to you in the past, that modulus is called the modulus of unilateral extension and compression. And it's greater than the Young's modulus. It's stiffer. The material is obviously going to be stiffer. When you don't allow it to bulge, when it's not allowed to bulge, it's going to be stiffer. And it's given by this expression, it turns out, in terms of the Young's modulus and Poisson's ratio. And you can show that that's greater if you look at that, play around, and respect that range. It's greater than Y. The speed of waves is the modulus, in this case, okay, there's a slash there, divided by the density. So these are the speed of purely longitudinal waves. That's the speed. For shear waves in a bulk medium with no boundaries, it's very simple. It's the shear modulus divided by the density. Now we're going to phrase everything here in terms of Young's modulus and Poisson's ratio. So it turns out that you can write the shear modulus like as this, okay? So here's the speed of shear waves in a bulk medium with no boundaries. It's interesting, I don't know if we're going to do anything with this, I can't remember, but it's interesting if you take the ratio of these two, Young's modulus drops out. So if you change the Young's modulus, you change these two speeds, but you don't change the ratio. Peculiar. Now, suppose we have a rod or a bar. Now we've got to deal with boundaries. And you know from 3119, right, the first course, that when the wavelength, so consider compressional wave, extensional wave on this bar right here. When the wavelength is large, you're going to have transverse motion, okay, because it's free. When the wavelength is large compared to the diameter, that's, I don't know if you remember, but that's what you solved for in 3119. There was an approximation there. The wavelength is large compared to the diameter here. And in that case, you can just use, it's just Young's modulus. The speed of the waves is just dictated by Young's modulus. The notation here is kind of weird. L is longitudinal, T is transverse. This E is extensional, I think. This refers to that. Okay, so let me end it right here, but let me say, so we have this rod where the wavelength is large compared to the diameter. We can imagine a rectangular cross-section, right? And so you can have these, obviously, and as long as the wavelength is large compared to this dimension and that dimension, you're going to have this speed of sound, speed of waves, right? But what happens if you have a plate here? So the wavelength is large compared to this size, but not. This is effectively infinite there. Now, do we get any motion like this? No. So it's going to be stiffer. The waves are going to travel faster. And so we'll pick this up tomorrow. It turns out there that for this, where the wavelength is short compared to this dimension, but long compared to that dimension, you get a different speed of sound. And if you play around with it, respecting that range of nus, you can see that it's greater than that value. And it's because it's stiffer. You've introduced some stiffness there that you didn't have before for this rod. Okay, we'll pick this up tomorrow. And then also, remember the geophone that I really build highly? Well, now, another very common thing, an accelerometer, a piezoelectric accelerometer. We're going to be spending most of the time tomorrow just looking at that one special case. Very important. And they're all over the place, piezoelectric accelerometers. Cars, ships, right? Okay.